Today we're going to talk about vortex lattice methods. Previously we had talked about lifting line theory, and that can be extended to a nonlinear lifting line theory to make it more generally versatile for a numerical method. We had just shown kind of analytic solutions. But an alternative and a popular approach is this vortex lattice method for numerical solutions of wings and multiple lifting surfaces. This is one we'll focus on in the homework as well. So vortex lattice method, you could think of it as multiple ways, like a panel code, a simple panel code, kind of a flattened panel code in 3D, or you could think of it as thin airfoil theory extended to 3 dimensions. So for example, if I have a wing, and let's just say a tail and maybe a fuselage as well, which we won't typically model in a VLM. Let's also put, like, say, a vertical tail. In the VLM model, we're going to kind of flatten these spaces into, and they could actually have sweep too. So let me just draw that. Let's say I've got a swept wing here, and I've got this tail and a vertical tail, but I'm going to keep the same plan form areas and shapes and sweep and all of that. I'm going to kind of flatten them like we would in thin airfoil theory. I'll still try to use appropriate boundary conditions, accounting for the twist on the sections and the dihedral, so I can have winglets. Let's add some winglets here on this wing. Sometimes people will add a flat section for a fuselage, kind of a sideways one, but if you want to get yawing moments, for example, it may be important, but we're going to really focus here on lift and induced drag. Okay, and so previously we had seen that we could take a wing, and I'll just draw a simple wing here, and we had built on this simple model of a horseshoe vortex and made many sort of concentric horseshoe vortices. Well, an alternative way to think of the same thing is that I could think of that rather than a nested vortices, I could think about it as some side-by-side horseshoe vortices. If I chose the strengths appropriately, it would give me the same result. But the side-by-side approach is a little bit easier for me to extend to think about, well, I guess you could think about it either way, but we'll think about it here as a side-by-side case for the vortex lattice. Here's a picture of what that might look like for half a wing here. There's going to be symmetric, so I'm just showing half the wing. We take a horseshoe vortex, but we can define multiple of them span-wise, as we've done normally. We can also vary them chord-wise. So here I've shown one at some chord-wise station, and I can have another one here at this chord-wise station, another one down here, right? So I can discretize my wing both span-wise as well as chord-wise. This method is flexible. I can have sweep, just as we've shown here. I can have dihedral and so on, twist, all of those things. So the method is pretty versatile, and we'll choose our coordinate system such that the trailing vortices, we'll define that as our x direction. We're going to have our trailing vortices extend back into the x direction. Previously with thin airfoil theory, I'm not sure if I derived this on the video, but I certainly do in the book. We had looked at a case where we had a wing, or sorry, an airfoil, actually I started drawing here, with parabolic camber. And we tried to figure out where to place a lumped vortex. So if we took all the vorticity was on that wing and we just lumped it all into one spot as a point vortex, where should that go? And where should we evaluate the normal velocity? And we found that the vorticity, or the lump vortex, should be at the quarter chord, and the control point, the location where we impose a requirement, our boundary condition, basically the normal velocity is 0, that should be defined at the 3/4 chord. So in other words, this is quarter chord, and this is 3/4 chord. Now, when we have chord-wise panels, we kind of build off that idea, and what we do is for each little panel here, we put the bound vortex at the quarter chord of that panel, and we would put the control point at 3/4 chord of just that panel. So this would be, this is getting a little hard to draw for size, but let me try here. Let's say that this dimension here is S, then we would call this 1/4 S. And then this distance here to where the control point is, that would be 3/4 S. So we're just basically utilizing that same idea, but extending it chordwise. In our case, we're going to simplify. We're not going to have chordwise panels, just only spanwise variations. This is also known as a Weisinger model. This is common for high aspect ratio wings, which is what most transport and many model airplanes and most general aviation airplanes are fairly high aspect ratio to where the chordwise variation in lift is less significant. We're mainly interested in capturing the circulation or lift variation along the span. As we've seen, what we're really trying to look at is things like, here's the back view of my wing. I want to know what that lift distribution looks like. As we've seen, that's going to affect obviously my lift, but also my induced drag. And so that's something I couldn't capture with my airfoil method, so I want to be able to capture this on my wing. The lift distribution also varies, in this direction chordwise, but that's generally of less interest. The variation is maybe less important unless I'm looking at things like, well, certainly for low aspect ratio wings, especially if I want things like pitching moments and so on, that can be important. But for many cases, I can get away with this. It's just span-wise variation. So that's what we're going to do here to simplify for the homework. X direction, as we've noted, is downstream. This is a standard aerodynamic coordinate system. X downstream, Y is out the right wing, and that gives, by the right-hand rule, Z positive up. That's fairly standard for aerodynamic systems. For dynamics, if you were doing a GNC class dynamics, it would be kind of the opposite. They typically do X as positive out the nose of the airplane, Y out the right wing, and so then Z by the right-hand rule will be down. There are also some subtleties right in the direction. For aerodynamicists, we usually think about the direction the wind is going. So this will be aligned with the wind, whereas for dynamicists, they usually align it with the body, which are not exactly the same, but we won't worry about that. Important thing for us is the X downstream, Y out the right wing. And so we're going to define a few things. We're going to define the location of these nodes. Notice once I define these nodal coordinates, that completely defines all of these horseshoe vortices, because they're just going to travel straight downstream in the X direction from there, and they'll just be connected straight between these nodes as shown. So I've got YI and ZI, noting both the Y and Z. Z would be up, so if I have winglets, I'd have a Z component, or if I have dihedral. And then I'm also going to define these control points. We'll call that YCP and ZCP, for example. Those will be my control point locations. I'm going to have N of these and N plus 1 of these, right? Just because I've got one at each end, so there's one more of those. All right, so as we've discussed, well, actually I have the model already. I basically just need to define a boundary condition. So I've got a model, which is I'm going to put in circulation, and as we've seen from our Helmholtz vortex rules, if this has some circulation strength gamma 1, that's going to be continued all the way along this horseshoe vortex. The next one is going to have its own strength gamma 2, which continues along its own one, and you can see these two vortices are going to partially cancel. So that's my model, and I need to decide what is the right strength for each gamma. Each sort of panel is going to have its own circulation strength. Well, to determine that, I need to enforce my boundary condition, which is that the normal velocity evaluated all the control points has to be 0, right? My no flow through condition. Or in other words, my free stream velocity plus my induced velocity, that's induced from all of the control points, that velocity dotted into a normal vector at each control point has to be 0. I'm just going to drop the control point, but we know we're evaluating each of these quantities at each of these control points, and we want to make sure that that normal velocity is 0 to satisfy my boundary condition. I could also write it this way. I'm just going to move this v infinity term to the other side just for convenience. We'll see. So I need my induced velocity at, say, my ith panel dotted into the normal velocity at my ith panel equal to minus v infinity at my ith panel, which typically is the same at every panel, but doesn't have to be dotted into my normal at my ith panel. Well, here's v infinity. We're going to have angle of attack. In general, we could also have side slip. We're going to keep it, again, simpler in this case. So using my coordinate system, I remember as we've drawn it, we've defined, well, we're actually aligning things here as follows. So this will be like this: cosine alpha, 0 in the y, sine alpha in the z. So I'm breaking this up into these components. This will be my x direction, this is my z direction. So I'm actually, by the way I've drawn it and I've kind of flattened it into the body, I'm going to call this x, this is z. So at least for as far as my horseshoe vortices go. All right, and then I need to also figure out what n hat is. I'm not going to do this in great detail, but we can see if I had, for example, dihedral, I'd want to account for that. So here's, let's say, some winglets that are not quite vertical. Let's call this phi, for example. This would be my back view, so this would be y, this would be z. And so I need to rotate that, or to figure out my normal components. In this case, this would be n hat, right? So I need to take the components of that. But I also need to account for the twist. So if I was to look at a side view of my wing, each section may have some twist. So here's my reference plane. This would be theta, is what we call twist. And so this would be, this is my x hat. Let's see, this is downstream is my x direction. And then this I'll just call this, I don't know, call this zeta, for example. And this would be, actually, I shouldn't have called this n hat. It's actually zeta hat because this is an intermediate reference frame. So this would be the zeta hat. And in that frame, I can now twist it. That would be vertical here. I can twist it. And this finally is my n hat. I need to account for both of those things. This is n hat normal to the panel. Well, if you do those two projections, what you'll find is that n hat is sine theta in the x minus cosine theta sine phi in the y, and then cosine theta cos phi in the z. So when I do the vortex lattice, I don't actually rotate my geometry with the twist. I do with the dihedral. I modify the dihedral because those are going to be large. But theta, I don't generally deform the shape of my horseshoes. I keep them going here in the x direction, not in this direction. I simply just account for it in the boundary condition. Okay, so let's see, something else here. I think that's good. Okay, so I have the components that I need. The only thing that I don't have really, and this is the hard part, is getting this, the induced velocity at each horseshoe vortex. I know V infinity, I've got n hat now, those are all fine. But I need to figure out the velocity that's induced at a single control point from all the other horseshoe vortices. Well, previously we had seen the Biot-Savart law. This gave me the velocity induced by a vortex segment, a vortex filament, we called it, and this was the formula that we saw. Okay, it looks something like this. And that just said, if I've got a vortex segment, right, and this is the direction of circulation, so dl is an infinitesimal segment, and I want to evaluate the contribution at some other location r, then I need to do this integral. I need to integrate along this vortex segment, and we did that integral, for example, for a straight line filament. But what I need to do now is I need to calculate the velocity from all of these segments. If I go back to the model, I'm at one location, one control point, and I need to calculate the influence from this segment and this segment and this segment and this segment and this segment, all of them. I need to sum it up. So we could say that the velocity at one control point is the sum over all j, summing over every other horseshoe vortex. And we're going to sum over a horseshoe at once. So we'll just have one gamma j. Remember, one gamma corresponds to 3 segments. We're going to sum over all 3 of them. But each one has the same gamma j. So we'll do for 4 pi, and I have to integrate over all 3 segments. And it's just the same formula, Rij cubed. Okay, so we could write this in a little more simple way. We could say, well, this gamma here, we could see everything is linear with gamma. So if I pull all of this out, all of this complexity, I'm going to say this is equal to the sum of j of gamma j times v hat ij. And v hat just contains all this complexity. In other words, it's the velocity induced by a horseshoe vortex with unit strength. So if gamma was 1, this would give me the v hat. And so then I just have to multiply by my gamma j's later. So I'm just going to leave it like that for now. It's going to simplify my math. So let's take this formula here, plug it into our previous slide where we had this thing, and expand that out. So I'm going to get, that gives me the sum of gamma j, v hat ij, dotted into n hat I equals minus v infinity. And I'm just going to drop the dot I because that's generally going to be the same, but it doesn't have to be, right? If I'm doing a maneuver or something, right, my velocity is going to vary, or if I've got some gusts, some span-wise variation in incoming wind, that could change, but we're not going to worry about that. Okay, so what we can see now that I have is that I could rewrite this as a linear system of equations. So I could say this equation here is as follows. AIC, we'll call this the aerodynamic influence coefficient matrix times gamma equals B. In other words, we can see this varies linearly with gamma, right? This is all just, this is like a matrix vector multiplication. This is a vector on this side. So you can say I've got a matrix times a vector equals a vector. This is just a linear system of equations. And if I look at this formula, I can see that AICIJ, in other words, the ij component of that matrix is just v hat ij dot ni. And my vector, the ith component of that vector, is just minus v infinity dotted into ni. Okay, so this I know, I'm going to have to get this, but I can see that once I do that, I can just assemble this matrix, solve a linear system, and I can compute all of my gammas simultaneously. So I will know what my circulation or lift distribution looks like along my wing. And now we've boiled this down to this problem. How do I get v hat ij? I need to get the velocity induced by a horseshoe vortex of unit strength at some arbitrary other location. All right, something in my throat. So here's a picture of that. This is a generic horseshoe vortex. It's going to, as we've seen, continue with the same strength everywhere. And by our convention, we've defined it so it extends, these Schrödinger vortices are aligned in the x direction. And I need to evaluate my velocity at some arbitrary location, control point x, which is some other location. Turns out these two vectors will be important in this derivation. R1 is the distance from the corner of this horseshoe vortex to that arbitrary location. R2, distance from the other corner. I derive this in the book. It's a little bit lengthy to derive, but works out fairly nicely. That this is the velocity induced at any arbitrary location. And you can see it's only a function of these two vectors, R1 and R2. That's all I need to know. Once I can define these, I can figure out what that velocity is. And this horseshoe vortex can be anywhere. This equation is a bit long, but it's because it's general, it's very robust. This can be anywhere, right? They could be on a wing and a winglet, a wing on a tail. They can be in any orientation, doesn't matter. This will work. If I have a planar wing, some of this will simplify, right? If I don't have anything in the z direction, I could simplify this a bit, but this is, not too hard to implement in this form. Okay, so how does that translate to what we need? Well, remember what we want to do is I want to evaluate the influence of some arbitrary panel or horseshoe vortex J, which I'm going to highlight here. So here's my jth one. Okay, so I've got one corner. We'll call this J X, or this is YZJ and YZJ plus 1. This is this one horseshoe vortex. And I calculate the influence at this other location, control point I. So these would be my R1 and R2 vectors from the previous slide. Or in other words, R1 is our control point I minus R2 J, right, where this one doesn't have the control point. So it's defining these nodes, and R2 is the distance going to the control point I from Rj plus 1. Okay, so once I've computed the geometry and I've just discretized and computed all these nodes and figure out my 3/4 chord location for all these control points that are halfway in between these control points, then I can just compute these R1s and R2s. Okay. Just a side note here, I've used uniform spacing. That's, one way to do this. So easy way to do it. There are other ways. I could use cosine spacing similar to what we've seen before with airfoils. And so, for example, with the wing, I may want to use cosine spacing so that I get panels that bunch up more. This is kind of not the greatest drawing here, but they're going to bunch up more here towards the tip, right? So my horseshoe vortices will be bigger at the root, and then they're going to progressively get smaller and smaller and be much smaller at the tip. And I do that because my lift distribution, remember, is changing much more rapidly at the tip. So if I was again to draw the side view here, like something like this, where this is gamma and this is y, and it's fairly flat inboard and then changes rapidly towards the tip. So I may want more panels towards the tip. Important thing to note if you do that the control points don't go in the middle of the panel. They go in the middle in theta space. So if you remember how to do cosine spacing as we use that cosine transformation we've seen. We take linearly equally spaced directions in theta, and then we transform it. We do the same thing with control points. We define these nodes at equal spacing in theta, and we define the control points in equal or halfway between them, and then we take the cosine transformation. The upshot is that when you create these panels and you'll notice they're getting smaller and smaller, the control point will be skewed towards one side. It's important to do this to do it that way. And you'll find that if you do this, you can, for example, for a typical lift distribution, get a more accurate answer in terms of lift and drag with far fewer panels. But this is simpler to do the uniform case, and that's what we'll focus on here. I should also note, again, that you should look in the book for details if you're interested, but that in almost every case, right, the wing is symmetric. Unless we're doing a case with, say, side slip, we're doing some sort of maneuver, then we want to actually retain that asymmetry. But in many cases, this is symmetric. I always still need to include the effect of the left half, but I don't have to solve for all the circulations on both sides, because whatever I solve here is going to be equal. It's going to be the same, just mirrored over on that side. So I only need n unknowns. I don't have to double it. You can keep my linear system smaller, make it more efficient. When I do that, I have to still account for all the vortices on that side. Again, you can look at the book for details if you want to do that. Finally, now that I can solve for all those circulations, what I really want to do is get forces and moments. We can do this with a near field method. I won't go into detail here. Again, you can see the book. This could be thought of as a Kutta-Joukowski approach. It's really derived not that way. It turns out to be equivalent to that. But basically, if you want to think of it as Kutta-Joukowski, I apply that locally using my far field values. Yeah, well, let's see, how much should I describe here? So here's my wing and the horseshoe vortices. And I can calculate, for example, using Kutta-Joukowski, if this is, let's just do it simple with V infinity. I can take rho, V infinity, crossed into gamma to give me my force, right? So I got V infinity, and I can account for rotation maneuvers, things as well if I want to. And I should say that this is going to be over each panel. And in fact, V infinity might change as well, but typically wouldn't. So I could do this. I get the velocity, I calculate circulation, I do the cross product, then I can rotate my coordinate systems for lift and drag. We're going to do it a little more simply. We're going to consider simple case here, but you could certainly do this in general, and this is a good way to account for maneuvering and circulation that's in different directions because of sweep and so on. But in our case, we're not going to look at asymmetry, so we're not going to have side forces, and we're not going to look at other moments besides the pitching moment. So this will be a little bit simpler. For lift, if we did that cross product, we would see, well, we would just get rho v infinity gamma by definition, right? Because lift is going to be perpendicular to v infinity by definition. So this cross product simplifies really well. And if I want the total lift, remember that I've got this, basically, I've got this discretized version of my wing. This is kind of my gammas, right? And this is y, because I've got these horseshoe vortices extending different circulations like this. Then if I want the lift created at a given panel, the lift at a given panel, we have to multiply by the length of that panel, which we'll call, well, actually, it's really just y I plus 1 minus yi, right? That's just this distance here. That would be the lift contribution from one panel. So my total lift is going to be rho v infinity times the sum over I of gamma I times yi plus 1 minus yi. Now we derive that really simply, but it turns out the same formula will work even if we have a swept wing, and even if I have dihedral. So if I have a swept wing, for example, again, see the book for details. I'm just going to do a quick motivation here. I have a swept wing, then my gamma actually has two components, this way and this way, and only this part contributes to the lift if I do that cross product. But my ds is actually getting longer because of the sweep, and those two things cancel out and I actually get the same formula. Also, if I've got dihedral, I have to be careful because, say here's a canted winglet here. My circulation on this winglet is also canted inward. So not all of it contributes to lift. So only a portion contributes to the lift. But it turns out that portion, if I take the cosine at angle, that's exactly what this gives me. It's just this y distance here. So although we kind of derive this really simply, it also works for cases of sweep and dihedral. And again, take a look in the book if you want to see that in a little more detail. Pitching moment, once we have lift, it's fairly straightforward using that same kind of approach. Again, the simplified approach that let's say this is my aircraft, and I want to calculate, whenever I calculate pitching moment, I have to define where I want to take it relative to. And typically that would be relative to, say, a center of gravity. And so let's say here's this wing and it's got some lift I at this point, force per unit length. I need to calculate what these distances are. Call this the distance in the x direction. And so the pitching moment then is going to be my lift, which we already saw was rho v gamma I times y I plus 1 minus yi. That's my L prime. But I need R cross L. And so that's going to be given by this angle here, which is exactly my angle of attack, because here's v infinity. This is my angle of attack. So that angle is the same as this. So when I do that cross product, it turns out that I need to include the cosine of the alpha. It's the sine of the angle between them from the cross product, but that's the same as the cosine of this angle. And I need my moment arm, which is just Rx. So my moment is equal to this. I've got a sum over I. And actually, I should have brought this out. This term here is constant, so I could bring that out of the summation. So sorry, I made that a bit of a mess. Let me write that one last time. Rho v infinity cosine alpha, sum over I of gamma I, yi plus 1 minus yi times Rx, which in general varies with I. The other thing I need to do is consider the sign. So for a positive lift, if I do R cross F, that's going to give me a nose down. And by convention, a nose down, we consider that a negative pitching moment. So I just put a minus sign up front. All right, so that's lift and pitching moment. The last thing we need is induced drag, and we're actually going to save this till next time. But what we're going to do, just as a preview, is we're going to use a far field approach, kind of like we did one of the first homeworks and some of those beginning lectures where we looked at if I did a momentum balance around a big control volume, I could find forces, especially drag, by looking at the momentum far downstream. And that's what we're going to do for this vortex lattice. This tends to be really convenient, even if I have multiple, especially if I have multiple surfaces, wings, tails, all sorts of things, maybe even multiple airplanes. I just have to look at what happens very far away, and I can calculate the drag of this whole system just by looking at the velocities in the far field. So we'll save that till next time.